So, let's talk about the image classification, the part 1, preparing the data and building the model in the previous lesson. Okay, so the goal of the lesson brings together everything learned so far. So the data loading, device handling, loss, and the weight updates to build first complete image classification model using MNIST and PyTorch. So the data set is MNIST, handwritten digits, training sets contains of 60,000 images, test sets consists of 10,000 images. Image size 28 28 pixels. Color grayscale pixels, color grayscale, one channel. MNIST is used because it's simple, well structured, and perfect for understanding full workflow before moving to more complex problems. Dia, lagay mo siya, Dia. Building the data pipeline, a Torch Vision, and MNIST. Torch Vision is PyTorch Computer Vision Library. It provides ready-to-use datasets like MNIST, image transformation utilities, automatic download, and organization. This removes a lot of boilerplate work and lets you focus on learning. So, transforms. Preparing images for learning. Two key transforms are applied. Number 1 is to tensor, converts images into PyTorch tensors. Scales pixel values from 0 to 255 from 0 to 1. Okay. This makes the data compatible with neural networks and stabilizes training. Okay, we are going to normalize them using the mean and standard deviation. It uses the mean of 0.1307 and uses standard deviation of 0.3081. These values come from the MNIST.
Plus 3 plus 3 plus 3 is 4 times 3.
So let's go.
9,
So
12. So
the normalization centers the data around 0,
Well
makes
done.
features
Now
scale
try
consistent,
this one.
helps
1.
gradients behave better. It speeds training. It speeds up learning. All images must use the normalization values so the model sees consistent data. So loading the dataset. So the key parameters here is the root is that slash data where files are stored. We're going to set the train equals true or false. Training versus test. Set. Okay. Download is equal to auto download if missing. Transform applies processing automatically. Training the and test datasets use the same transforms to ensure fairness. And number 3, data loaders and let's talk about data loaders and batching. Training data loader. Batch size equivalent to 64. Shuffle. True. Why do we need to shuffle? It's because we're going to it makes sure that we prevents the model from seeing digits in a fixed order. Avoids learning dataset order instead of digit features. Ensures each batch contains mixed classes. Test data loader. Wala naman.
Tawagin mo si Lia.
Ano ba yung ano? Di ba hindi nila alam yan?
Si ito.
Sino yan?
Ay, napabuksan. Sige na. Church mo. Pa-church ako. Gawin ako. Mamaya, lalaro.
Sarado mo nga yun.
Ay, pinapakanta nga ako ni Nana.
So the test loader, like for examples, let's talk about the training mode data loader. So batch size equals 64. So shuffle it through. When we shuffle, we prevent the model from seeing digits in a fixed order, avoids turning dataset order instead of digit features, ensures each batch contains mixed classes. So the test data loader, batch size is equivalent to 1000, shuffle is equivalent to false. Why different? No grades are computed during testing. Order does not affect evaluation. Larger batches improve efficiency. Shuffling is unnecessary because the model is no longer learning. Understanding the input shape. A single MNIST image tuple is equivalent to 1, 28, 28. A batch of 64 images is 64, 1, 28, 28. Problem: linear layers cannot process two-dimensional images. They require flat vectors. Flattening the images, why? Flatten is required. Flatten your shapes. 28 by 28 is equivalent to 784. So the batch becomes 64 and 784. Why 784? We multiply 28 by 28. So without flattening, PyTorch raises the shape mismatch errors when passing data into linear layers. Building the neural network. Instead of sequential alone, a custom model class is used, inheriting from NN.module. Parameter tracking, gradient handling, access to PyTorch training utilities. Model architecture. 1. Flatten, linear, 784 to 128. 128 hidden features. ReLU is the adds nonlinearity. Its activation function keeps positive values, zeros negatives. Linear 128 and outputs one value per digit 0 to 10. That's 0 to 9, I mean. The output size is 10 because there are 10 digit classes. Forward method defines how data flows: input image, flatten, pass through layers, return predictions. This method is what PyTorch calls during training and evaluation. What the model can and can't do now. The data is loaded and pre-processed. Batching and shuffling are set up. Neural network structure is defined. But the model has not learned anything yet. It cannot distinguish digits meaningfully. The weights are still random. What comes next? Okay, so we are going to have the optimizer, trailing loop, forward pass, loss calculation, propagation, show accuracy, improves over time. So to summarize, these lessons: preparing clean data and building a correct model structure. Nothing is stringent, but everything is placed so learning can happen correctly in the next step.